This video is going to discuss the second derivative test, which is another way of classifying local extrema in certain scenarios, and also an application of the first and second derivative tests in problems that are known as optimization problems, where you are asked to find a maximum or minimum value of a function in a real-world scenario. Okay, second derivative test, again, it's going to classify local extrema, but as according to the name, we're going to use the second derivative. Okay, so here's the statement of the test. Okay, so we have to have a critical point of the function occurring at an x value. If the second derivative is positive for that critical number, or critical point, for the x value of the critical point, then it has a local min. If it is negative if the second derivative is negative at that critical point, then it is local max. Notice, okay, this fails if f double prime of c is equal to 0. That type of point is going to be called a point of inflection, which we're going to come back to at a later time. If it does fail, then we have to use the first derivative test. Okay, so this test typically is faster to execute than the first derivative test, but if it does fail, we need to go back to the first derivative test. Okay, a pictorial way of summarizing this test is via two of my friends. They're called Maxi and Minnie. Okay, so Maxi, imagine this is the face of Maxi. Okay, and this is the face of Minnie. Maxi is a very sad person because he's reached his maximum. Minnie's at her lowest, but she's still happy. So the way to remember this is if f of x has a maximum at x is equal to c, then the derivative at this is 0. Okay, and on either side, the concavity, or the second derivative, the sign of the second derivative should be negative. Okay, for Minnie, if we have a minimum, and then the second derivative, or the first derivative is 0, and the second derivative would be positive at that critical point. Okay, just a couple ways of remembering this test. Okay, so let's see this in a problem. We want to try to use this method to classify extrema of this function. So first I need to find the critical points. Okay, so that is finding the first derivative, and then I need to set it equal to 0. Finding the first derivative, I get 6x cubed minus 12x squared plus 6x. Factoring this, I get 6x and then x squared minus 2x minus 1, which, if I set this equal to 0 now, I get x is equal to 0 and 1. Okay, so those are going to be my critical, those are going to be the x coordinates of my critical points. Okay, and so if I find the critical points, it's 0 and 1. Put in 0, I get 0. Put in 1, and I get out 0.5. Okay, so those are my critical points. Okay, now I want to compute the second derivative in hopes of classifying these right off the bat. So f double prime now, this is 18x squared minus 24x plus 6. Okay, and I'm going to factor this just because I have a habit of factoring. 6 parentheses 3x squared minus 4x plus 1. Okay, now if I compute f double prime of 0, okay, this is just going to be 6, which is greater than 0, so this tells me automatically this is, okay, second derivative was positive. This is my friend Minnie, and So this is a local minimum of 0 at x is equal to 0. Okay, got one of them done already. Okay, then let's compute f double prime of 1. If you do this calculation, you actually end up with 0. So here, second derivative test fails. Okay, so what I want to do now is I have to revert to the only other tool that I have to find critical points, which is the first derivative test. So use first derivative test. Now, had this not failed, I would have been done with the problem in terms of finding the local extrema. For the for globals, I'd still need to look at the endpoints and whatnot. So let's just go through the first derivative test. Okay, so I already have my critical points, so I can make a sign chart for f prime and f. So let's see, here my endpoint is 3, that is inclusive. So that's 3, and then 0, 1, and 2. 2 is exclusive. Okay. Now here, if I'd have to say take f prime of -1, f prime of 0.5, and f prime of 1.5, and compute their signs. When I do that, this ends up being negative in here, positive, and then positive here. Okay, so this means that the function is decreasing, then increasing and increasing. So actually here, there's going to be a saddle point of 0.5 at x is equal to 1. Okay, now, so I've classified my local extrema. Okay, for globals, again, globals I need to look at, say, I need to make a list of the x comma y pairs of my critical points, and then the endpoints. So -3, this ends up being 256.5, and 2, 4. This is exclusive though. Okay, now from these values I would want to pick the largest for the global max. Okay, but here there's no global max. Okay, why is that? Well, even though we would think this value, since it's the largest, is going to be the global max, notice that at the end here, it is increasing. So technically, I guess, since if we actually, let me redo that. Even though we do not have the second endpoint at 2, okay, its value would be 4. However, it is still smaller than this. So actually, yes, this is a global max. So this is a global max of 256.5 at x is equal to -3. And then similarly, the lowest value, which is here, this is going to be a global min of 0 at x is equal to 0. Okay, then that's an example of using a second derivative test, and just keep in mind, second derivative is really easy to compute, and then you just have to substitute in to determine local min and max. If that fails, which in this case it did for one of the critical points, then you have to go back to the first. Alright, now, optimization type problem. We're given a scenario And in that scenario, we're asked for a maximum minimum oxygen content. Okay, that means I need to find the local mins and maxes and classify them. Okay, let's try to do the second derivative test because it's going to be a lot faster than the first derivative test. So C prime, computing this, is negative 3t squared plus 60t, and I'm going to factor it because I have a habit of doing that, minus 3t, t minus 20, and if this is equal to 0, that gives me critical numbers of 0 as the x-coordinate and 20, and these end up being 600 for the concentration and 4600 for the concentration. Okay, so I have my critical points, and then now I can find the second derivative, and hopefully that'll cooperate. And let's see, so it's negative 6t plus 60. Put in 0, so c double prime of 0. This is equal to 0, so second derivative test fails. And put in 20, and put in 20, this is going to be less than 0. Okay, so this is a local max of 4600 at t is equal to 20. Okay, so again, maxi would be the case where second derivative is negative. That means you have a maximum. Okay, but so I have a local maximum. I need to I want to fully classify everything, so I need to know about 0 and the endpoints. So I definitely need to compute, or I need to do the first derivative test. Okay, so c prime and c, let's see, then 0. This is inclusive, 20 and 30. Okay, and the signs here, if you take test values, says c prime of 10 and c prime of 25. This ends up being positive and negative, so it goes increasing to decreasing. Okay, well that doesn't help me classify 0 and 30, so this is where I need to do the method for global extrema. Okay, so I compute c of 0, c of my critical point, so compute the concentrations at endpoints and critical points. So this is 600, this is 4600, we knew that already, and then doing this computation, you get 600 here. So I would actually say this is also a global max, and each of these other ones are global mins. Okay. Alright, so we've classified those, and then the last thing is find when the concentration is increasing the fastest. Now this isn't completely obvious. This is asking us to find a point of inflection. Okay, so when it is increasing the fastest, this is a point of inflection, which is when the second derivative is equal to 0. Okay, so let's go down here. So increasing fastest at point of inflection. Okay, so that's c double prime is equal to 0. Okay, and so that's negative 6t plus 60 is equal to 0, or t is equal to 10. Okay, so I would respond, it is increasing the fastest
t is equal to 10. And here we aren't given time units, but that would be sufficient. Okay, and so that's some examples of optimization and the second derivative test.